In this video, I want to explain a little bit about how dual vectors actually behave. The defining property of a dual vector is how its components transform under a coordinate transformation. So here I'm going to write the components of the dual vector in the transformed frame, which I'm just going to denote here by primed, is equal to dx mu, the original coordinates differentiated with respect to the new coordinates, times the components of the dual vector in the untransformed frame. And so here, just so you know, mu can sort of take on values 0, 1, 2, etc., depending on the number of dimensions in our problem. And remember that the way in which dual vectors transform is essentially the opposite way to how vectors transform, where the derivative here is the derivative of the new coordinates with respect to the old ones. Okay, so that's the first thing about dual vectors. What else do we know about them? Well, the idea is that they act on vectors, and if they do so, they produce a number. In other words, a scalar. So the idea is that a dual vector essentially eats, by eats I obviously just mean acts on, doesn't actually eat it, eats a vector to produce a number, and by that I mean a sort of real number. So the idea here is that if we take the components of our dual vector and then we act on a vector, v mu, implicitly here we're using the Einstein summation convention, then what this produces is a real number. And when we actually do this kind of calculation, this is essentially what is known as the inner product of the vector v and the vector w. Now, the reason I'm saying the vector w now is because of the fact that essentially if we were to write w dot v, where both of these things are vectors, then the way in which we would actually work out that inner product is by then transforming the vector w into its dual w mu, and then we could work out just the inner product pretty simply, just by summing the individual elements multiplied by one another. So what does it suggest? Well, it suggests that actually what we could do is we could represent the components of a dual vector in a row vector, so that's sort of w0, w1, w2, etc. And then we could represent the components of a vector in a column vector. So here we have v0, v1, etc., all the way up to sort of vn, if you like. And then if we were to sort of just actually multiply this out, then we would actually get just what we had before, w mu times v mu, which will, as you can see here, quite clearly just represent a number. So what is an example of a dual vector? Well, a typical example is the electric field, call it E mu. If we then multiply that through by some infinitesimal displacement, call it dx mu, and then we multiply this by -1, then essentially what this gives us is the work done in moving a unit charge through a distance dx. So we see here that E mu is our dual vector, whereas dx mu is our actual vector. Finally, we can think about what a dual vector actually represents geometrically. It turns out the way to think about dual vectors is by visualizing them as something which is known as one-forms. I don't want to go into much detail about one-forms here, other than to say the way in which we are thinking about visualizing a dual vector is as a one-form. And the idea here is that what we can imagine is a series of parallel surfaces, something like that which I'm drawing now. So each of these individual surfaces in our electric field example might represent surfaces of equal values of the potential. So this might be phi is 3, phi is 2, and phi, this final one here, is phi is equal to 1. So each of these individual surfaces represents a surface of constant values of the electric potential. So these collection of surfaces here actually represent what is known as the sort of one form representing the electric field. So then what we can do is we can use this one form to act on a vector. So here what we do is we draw our sort of vector as going through these various surfaces and then eventually piercing the last one. And so just for clarity here, this red line here is dx mu. And essentially the number of surfaces that this vector actually passes through or punctures is what represents the work done. So we can see here that we represent a vector or a contravariant vector just as a line, and a one form we represent as a series of parallel surfaces. And then if the one form acts on a vector, we're essentially counting the number of these parallel surfaces which the vector punctures. So if we had a stronger electric field, then we would have a higher frequency or density of these surfaces. So we might represent that similarly to before by just drawing a series of parallel surfaces, although now we're just going to imagine that they're much more densely packed than they were previously. So we just have something that looks like this. And then if we then use the same vector which punctures through these various plates, then we're going to see that this is going to pass through many more plates than it did previously. And hence what we have here is we have a higher amount of work done.